this first section in the conics and parametric and polar chapter is just a opportunity to get you refamiliarized with the conic sections. And conic sections are the conic sections are found by taking basically what looks like an hourglass figure. So we have a cone and an inverted cone, and slicing it certain ways. So if you look at this animation here, when we slice it, we're slicing it with that green piece of paper, I guess we could call it. And so if we notice as this goes through, we're going to slice it vertically, parallel to the axis. So here's the axis of the hourglass, or the inverted cone. So there's a vertical slice parallel to the axis. That gets us a section above and below. There it is. And then we can slice it parallel to the edge of a cone. We can slice it parallel to the bottom. Or that last one, we can slice it that's not parallel to anything, but is at such an angle that it doesn't intersect the upper cone. And so that gets us our 4 conic sections. So if we kind of look at each one of those, I freeze-framed the animation to look at each one of those. Here, this one is parallel to the bottom or to the top. Technically what it is if this is the axis of the hourglass shape of the conic, it's really perpendicular to the axis. That's technically how they categorize it. But it's basically parallel to the bottom. So as we're cutting it across like this horizontally, we can see we get the circular shape. We get something that is a similar shape to the bottom. We know the bottom and the top are circles. And so we get the similar circle. It's just a little smaller. Here we're going to, again, here's the axis of the conic. We're going to slice it at an angle that is not drastic enough to intersect the top cone. So if we have this skewed slice here, then basically what we're doing is we're elongating the circle, and so we have this elongated circle, which is an ellipse, and so where the circle has a constant radius all the way around, the elongated circle has a major axis and a minor axis that we have to pay attention to. And so at this point, this is at some angle theta that is basically less than the angle of the edge of the conic. And so, you know, when we talk about that angle theta, it would be kind of like, you know, this would be that angle theta. This next one, we again, if we have the axis of the conic here, the axis of the conic looks something like this. So we have now a slice that's parallel to the axis. And when we slice parallel to the axis, we're going to get something that has 2 components to it. And so when we have that double component, that's a hyperbola. And then the last one is parallel to the edge of the conic. So here's the edge here. This, you know, this is constituting the edge. So here is the axis. And the axis and the edge have you know, some sort of angle here. That angle is duplicated here, and we get this parallel to the edge cut. And when that happens, we get our parabola here. So in this case, theta would be equal to the angle of the edge. And those get our 4 conic sections that you've studied in either Algebra 2 or pre-calculus or something like that. In addition to those 4 slices, we can also slice it 3 more ways. For instance, if we slice it and it happens to go through this point here, so if you could picture, and this is something the animation doesn't do, but if we could picture this, any one of these slices really going right through the edge here. Basically what we've done is we've taken this enclosed shape and collapsed it. So if you could picture this green piece of paper sliding vertically upward until it gets to this point here, the circle would get smaller and smaller and smaller and smaller. Likewise, the ellipse would get smaller and smaller and smaller. So as that's doing that, as it's going to this point here, that piece of paper is basically, you know, coming across like this. And so it's coming through just at that point there. So that circle or that ellipse is kind of collapsing on itself and goes to a point. We call these degenerate sections because they don't make a shape; they just make a point or a line. If we take the parabola, so for this one, it's either, you know, the circle or the ellipse collapsing. So this would be the circle or ellipse collapsing. Here, if we take the parabola and we cut it, and we move this green piece of paper up to the edge here, then we'll have the edge of the paper just going right along the right side of this cone and the left side of that cone. And so as that happens, then that green surface is really just tangent basically to the edge of the cone. So it's touching that cone in a single line. And so this is kind of the collapse of the parabola. And then likewise the hyperbola here, as we look at collapsing this on each surface, we can get then this shape here, which ends up being still linear shape, but it ends up being the absolute value of a line. So we end up getting that V shape. And so these are the three degenerate sections because they don't get us these curved two-dimensional figures that we know as conic sections, but they are technically slicing a conic, so they technically are categorized as conic sections. If you have a TI 84 in your apps, you have a preloaded program to graph circles, ellipses, parabolas, and hyperbolas on your graphing calculator. And you can graph them in one of two ways. If you have the equation in what we call intercept form, where we have an H and a K, and for a circle that would be the center, for an ellipse that would be the center with the major and the minor axes. For a parabola, the H and the K represent the vertex of the parabola, and same with the hyperbola. Then you can graph them, it'll show up on your graph screen. Likewise, you can also graph them if you have it in standard form, if you have the circle in standard form, by knowing those coefficients. And you probably went through some pretty rigorous graphing of conic sections in Algebra 2 or Pre-Calc, and we're not going to go through that rigorous graphing, but we are going to work on getting things into vertex form by completing the square. But if you don't have this app on your graphing calculator, I have it on mine. You can stop by and I can load it onto yours, but it's a quick way of graphing conic sections. So if we we'll start looking at the parabola here. So when we talk about graphing a parabola, we can either have a parabola that opens up and down or a parabola that opens side to side. And so a parabola that opens up and down is a function. And so this parabola here, if you notice, this one has y squared equals 4x roughly, and this has x squared equals 4y. And so if we look at that, then this is the type of parabola here that would open either up or down. It's an x squared. Or we could have it opening up, but have its vertex below the axes. Likewise, we could have it opening down and have its vertex above the axis. So these are all functions. And so if we look at that real generally it's y equals x squared. So that's our function. These are not functions. This is x equals y squared. So these are all going to open like this, or like this, or can even cross over the vertical axis. So the vertex could be something like this, or the vertex could be something like this. But if you do the vertical line test on these, you can see it crosses that that relationship in two spots. So these are not functions. To graph these, if you don't have the the preloaded program, you'd have to actually graph the positive square root and the negative square root to get the full relationship. Once you break those positive square roots and negative square roots up, then you do have a positive function and a negative function. So the key though is to, as if you're identifying what type of conic section it is to look at the powers. So we have x squared and we have y to the first power. We know that's a parabola when we see that relationship on the that polynomial relationship, that relationship on the powers. And so if this one we solve this for x squared, so it's looking like this, then it looks like x squared equals minus 8y. And then if we get it into this form, then what we have here is, if I just kind of do an intermediate step here, I really have x minus 0 squared equals, now I have to make negative 8 by doing 4 times a number. So it would be 4 times negative 2, that would be my negative 8, times y minus 0. So h comma k, which is our vertex, is going to be 0 comma 0. So that's right here. And then this negative 2 means that the focus is located 2 units below the vertex. So the focus is right here. And then we can graph the parabola there. So we're looking at that focal point right there. And parabolas we actually have a lot of common uses for parabolas. The idea is that the focal point is the point that if we go from the focal point to any point over here, and then we do a symmetrical line over here, those distances are the same. Parabolas' practical applications are things like satellite dishes. And if you think about a satellite dish, it's kind of like this. And then you have this little thingy that's kind of suspended in the middle of the satellite dish, and that little thing is the receiver. And so what happens is that, and this is getting a little physicsy, but we'll go there anyway, is when a signal comes in and hits the dish, then when it bounces off the dish, it goes through that focal point. So it doesn't matter where the signal comes in, as long as the dish can catch it, it will go through that focal point. And so if you put the receiver at the focal point, then the receiver can receive the signal and send it through your coaxial cable into your television. So that's how we it's one practical application for parabolas or parabolic shaped surfaces. Another practical application that you probably use a lot of is a flashlight. And the same thing, that mirrored dome is a reflective surface, and headlights on cars are used the same way, and they just kind of reverse this this whole idea. So if we look at a flashlight, we have this dome shaped, and the inside is reflective. It kind of looks like glass, or a mirror, excuse me. And then usually what happens is there's a small hole at the back of this thing, and we stick a light bulb through here. And what happens then is when that light bulb shines, the light goes out in all directions, and when the light hits the mirrored dome, it gets sent out horizontally. That's the reflective properties. And so what happens then, it creates a beam of light. So it kind of reverses the satellite, where this is a signal coming in and this is light going out. And so that's how we use parabolic shapes in flashlights and headlights, to create a beam of light so that we can see out, instead of just walking around with a bare light bulb. When talking about an ellipse has a major and a minor axis. So the major axis is the long portion of the ellipse, and the minor axis is the short portion of the ellipse. And so the major axis is defined as A. So this is where if we have the A underneath the X, then the major axis is parallel to the x-axis. So this type of form of, and again, this is like a vertex form, would give us an ellipse that looks like this, where the major axis, the wide portion of the ellipse, is parallel. So here's the major axis, here's the minor axis that's parallel to the horizontal axis. When we see that the bigger number is underneath the y-squared expression, then we're looking at an ellipse that stands tall, so to speak. So where the longer portion is now parallel to the vertical axis. The first thing to kind of know is to kind of identify the orientation of the ellipse. The next thing is to write it in this vertex form. The H and the K is then the center. So this point of the ellipse is H comma K, and likewise this part is H comma K. And so that's the vertex of the ellipse, or the center of the ellipse. And then out from the ellipse, then we go distance A to the left and A to the right if the major axis is horizontal, B up and B down. And then we rotate that for if the major axis is vertical. We go up and down A and left and right B. The ellipse is defined as basically taking a string and putting the string at 2 points, and those 2 points are called foci, and that foci is this distance, and this kind of looks a little Pythagorean-like, but the foci are that far from the center, from the vertex of from the center of the ellipse. And if you notice, it looks a little bit like a Pythagorean thing, but it's got a minus sign here, which is important because that means this value of C will always be littler than A. And so if we look at that, then if we have kind of an ellipse here, I'll just deal with a horizontal ellipse. If this is the center, then the foci are kind of here and here. They almost look like the focal points if it were a parabola, like this. If we look at this and said, oh, let's kind of look at that as a parabola, this would be the focal point. And likewise on the other side. And if we connect, the definition of an ellipse is if we connect the foci to a point on the ellipse and then go to the next foci, that's a constant distance. So if we would pick a different point on the ellipse, like right here, those two would add up to the same distance. Or if we picked another point over here, then those two would add up to the same distance. And so basically what you do then is, to draw an ellipse, is you take a piece of cardboard, okay, and you put 2 tacks on your cardboard, and then you hang a string that's longer than this distance so that it's slack, and then you can make the string taut and go all the way around, and that will get you an ellipse. The eccentricity is how oval it is. So if we look at this, the eccentricity is basically how close is this value C. You know, C is basically the distance from the center to that purple point, that foci. How close is this to the major axis? So, so the idea is, you know, C can't be bigger than A, so we have a maximum eccentricity of 1. And we can have a C of 0. If we have a C of 0, then we have an eccentricity of 0. And so this is the ovalness. Okay, so an eccentricity of 0 means no ovalness. No ovalness. Which means if there's no ovalness to it, then it must be a circle. And then an eccentricity of 1 is basically the ellipse collapsed on itself, and it's a line where your C and your A are the same values. So your C is way out here, which means you just have basically a line. You've collapsed your ellipse. And so if we look at graphing an ellipse, this is where that app on your graphing calculator really comes in handy. But if we look at graphing this ellipse, really what we're doing is we're looking at an exercise and completing the square. And so to set this up, we're going to group all our x terms together. So we have a 36x squared, we have a 48x, so plus 48x. And then we're going to get all our y terms together. So we have a 9y squared and a minus 36y. And whenever we complete the square, we always, if there's anything else left over that doesn't have a variable, we take it to the other side. So that's going to equal a minus 43. And then we work on completing the square. So when you want to complete the square, the easiest thing to do is factor out and get this coefficient to 1. So really what we're looking at is 36 times the quantity x squared plus, and if I factor out a 36 here, which is tough to do, but if you take 48 divided by 36, you get, you end up getting 4/3 x, and then we have to insert some information to complete that square. And then we're going to factor out a 9 here. This one's a little easier. It's not a fraction. So we're left with y squared minus 4y plus something to complete that square. And that equals negative 43. And if we're going to add something to this side, then we have to balance it by adding something to that side. And we've done that twice. We've got to complete the square for the x and the y to get it in vertex form. So we're also going to add something for the y completing the square. So if you remember completing the square, okay, completing the square means take the b, so take, I'm going to work on this one first, so take the b term here, the minus 4, divide it in half, so that equals minus 2, and then square it. So minus 2 squared is a positive 4, so we're going to add 4. In this case, and that means I got to balance it by adding, well, let's talk about balancing in just a second because it gets a little more complicated with a coefficient out front. Okay, so we have to take this and cut it in half. So half of 4/3 is 2/3, and squaring 2/3, so let's take 4/3. Divided by 2, that's like multiplying by a half, so that equals 2/3, and square it. 2/3 squared is 4/9, so this has to be 4/9. Okay, so there's our completing the square. Now we've got to figure out what to add to the other side. I'm just going to make this a little tinier so I can have some space here. Okay, so there's our completing the square exercise. Okay, so really what did we add to this side? Well, we added a 4 inside brackets. So we really added 4 times 9, which is 36. So that means we're going to have to add 36 to the other side. Here we really added 36 times 4/9. So 36 divided by 9 is 4, times 4 is 16. So we really added 16 to that side for the x completing the square. So we're going to have to add 16 to this side. And then we're going to go ahead and write this as a perfect square. So we've got 36x, and it's going to be a plus. And then what we put here is basically what we had cut in half, so x plus 2/3. And then for the next one, it's going to be 9y, and this is going to be a minus because there's a minus sign here. And what was this cut in half? This cut in half was -2. So y minus 2, quantity squared. And I just realized I forgot to square that quantity there. And then on the right-hand side, we're just going to do the math here. When we add those 3 things together, we end up with a 9 on that side. So one format then, when we're looking at this vertex format here, the key here is to get 1 over here on the right-hand side. So in order to do that, we're going to have to divide by whatever's over here, which is 9. So we're going to go ahead and divide by 9. And when we simplify that, we're going to end up with 4x plus 2/3 squared plus y minus 2 quantity squared equals 1. Okay, so there's our parabola. Now our parabola really is written, in order to identify the major and the minor axes, we need to get this over a squared and get this over b squared. So at this point it becomes some algebraic stuff. This is kind of a difficult one, but it's, you're not going to see much more difficult than this, that's for sure. So when we look at this, we can take that first completing the square and rewrite it as x plus 2/3 squared divided by, because multiplying by 4 is really like dividing by 1/4 by the reciprocal. And so there's your a squared. And so we'll get to rewriting that in a second. And then the next one looks like y minus 2 quantity squared over 1. And then that equals 1. So now we have them written as fractions. And then I'm going to write them as perfect squares down here so that we can see the value of the a and the value of b. So in this case, this is going to look like then x plus 2/3 quantity squared over 1/2 squared. And then this is going to look like y minus 2 quantity squared over 1 squared equals 1 squared. Or equals 1, excuse me. So now I can pick out my h and k. So when we're looking at finding the center of the ellipse, our h is over here. And so the format is that those things in the brackets have to be minus signs. So really what we want to do is we want to come in here and get rid of that plus sign and rewrite it as minus a negative. And that almost looks like an equal sign, so let me redo that. Minus a negative, there we go. So we know that the center then is minus 2/3 comma 2. So we're going to go over 2/3 and up 2. So there's our center. And then from there, we're going to find our major axis. So our larger number is under the y. So our major axis, our a value is 1, and our b value is 1/2. So since this is under the y, we're going to have to go up 1 and down 1. So we go up 1 and down 1 to get the edges of the parabola. And then for the b, it's left and right because it's under the x variable, so we go left 1/2 and right 1/2. And so there is our ellipse. It's pretty tiny. So there's the ellipse that has that equation right there. Another kind of look at this is we have the foci here of 0, 5, 0, minus 5, and a major axis of length 14. Okay, so if this is the case, if we look at this graphically here, and the foci are 0 up 5 and 0 down 5, then we know this, this ellipse is vertical. Okay, and it's got a major axis of length 14, which means 2a, because a is the major axis variable, is equal to 14, so a is 7. Okay, now the center is going to be halfway between these things. So halfway between these things is right at the origin. And then if we have an a of 7, that means we go up 7 and down 7. And if a is 7 and c equals 5, that's the distance to the foci, then we have to figure out what b is going to be. So if c is 7, we got 7 squared. A is, excuse me, c is 5. I made a mistake there. C is 5 squared equals a squared, which is 7 squared, minus b squared. Okay, and so doing the math on that, we've got 25 equals 49 minus b squared, so b squared equals 14. Nope, 24. I can't subtract. There we go. B squared equals 24. And so b is the square root of 24. And so if we want to put it then in that standard form for x minus h squared over a squared plus y minus k squared over b squared equals 1, then that's going to look like, these are going to be zeros, so it's going to be x minus 0 quantity squared over my value for a is 7, and y minus 0 again, and my value for b is the square root of 24, and I'm going to have to square that. And so that makes the square root of 24 squared, it makes it, you know, be not so bad there. So we got x squared over 49 plus y squared over 24 equals 1. So there's that vertex form of that parabola. The ellipse and the parabola are pretty much the two really common things you'd be asked to graph. Graphing a hyperbola is really rare. You have to go through the same steps to complete the square so that you get it in the standard form. And so one of the things to kind of acknowledge is that with the ellipse, let me just go back to that standard form. We've got a plus here, and then we've got x minus h and y minus k both squared over a squared over b squared. And this looks very circular for a good reason that I'll get to in just a second. For her hyperbola, that changes to a minus. And then you have some lines, some asymptotic lines that you have to worry about graphing. It's pretty involved and it takes a while, so we're not going to worry about graphing it, but you'd have to go through and complete the square, and then we'd have to come up with those equations for those asymptotic lines. And that's better left to the app on your graphing calculator. Circle is something you should be very comfortable graphing, and if you notice, if we go back to the ellipse, since the ellipse is just basically a squashed circle, or an elongated square circle, however you want to look at it. When we talk about major axis and minor axis, you know, when we talk about an ellipse like this, well, a circle is just basically saying, you know, let's take this major axis and this minor axis, right? So here's the 2a and here's the 2b. Let's make those identical. So here's your 2b and here's your 2a. So in this case where we have 2a is greater than 2b, here we have 2a equals 2b, and we have a circle. And so if these two things are equal, then, and I made a mistake here, if this is an ellipse, this would be a 1. So if a and b were equal, as the case is with the circle, then we could multiply through and just get a constant over here. So if they're equal, then we're just going to call it a radius. And if we call it a radius, then we can just multiply through by r squared, and if we do that, we multiply through by r squared here, so we multiply by r squared, we multiply by r squared, we end up with equaling r squared. And so with the major and minor axis being the same value, you end up reducing your equation down to the equation of a circle. So that's how we get the equation of a circle. And the h and the k are still the centers. So just to kind of recap here on that graphing calculator app, that's probably the most effective way of graphing these things quickly. So like I said, if you don't have that app on your TI-84, let me know. I can bring in the cables and we can get that downloaded on your graphing calculator.